It talks about information-based complexity results, and today will be the second part of this talks by Erich Novak, and today is the last part too. So if you have any questions concerning this, ask today. Okay, Erich.
Okay, thank you very much. I mean, you can ask also later, so I will be around for another 4 weeks. Okay, welcome back to information-based complexity. This is part 2, and this part 2 is mainly about numerical integration. So the problem is to compute the integral, and in most cases it is just like this. So we want to compute such an integral, and we ask the same kind of questions like the day before yesterday, namely we ask how many function values do we need to compute the integral up to some error epsilon. And again, I mean, this was really the basic assumption. You need a function class fd to fix in advance, otherwise the whole problem of complexity does not make sense. So you cannot compare two algorithms if you do not indicate a class of functions, because always one algorithm will be better than the other algorithm for certain integrals and vice versa. So you have to fix in advance a class of functions, and this is somehow the message number 0, I guess. Otherwise you cannot speak about theoretical results in numerical analysis. So I will, in most cases, I will have such a normalization. So we know the integrals, the true integrals are between -1 and +1, and so this does not depend on the dimension d, for example, and so it makes sense to discuss tractability and the curse of dimension, and we do not really have to distinguish between the absolute error and the normalized error, because we have such a normalization in advance. I will study as well deterministic algorithms and also randomized algorithms, also called Monte Carlo methods, and maybe just a small remark. Many of the results of this talk would be similar for optimization also, or for approximation. So sometimes we get different constants and so on, but somehow the results are quite similar, but not if we consider randomized algorithms. So it is really for randomized algorithms, it makes quite a big difference whether we study integration or approximation or optimization. So I mean, as a first rule, maybe, I mean, which does not apply always, but usually randomization helps quite a lot for the problem of integration, but it does not help a lot for optimization and approximation. But of course there are exceptions from this very simple rule. Okay. So again, the information complexity here is we count the number of function values that are needed by an optimal algorithm to obtain an error epsilon for all elements from the given class fd. This is what we call information complexity, and this is the basic quantity that we want to study. And sometimes, I mean, in numerical analysis, it is more common to to speak about optimal error bounds, but of course this is just the inverse function. So here we take the infimum over all algorithms that take n function values and take the sub-error, the maximal error over the class. Of course, this is now here for deterministic algorithms. We have to modify this a little for randomized algorithms. And I want to give us some results, some known and some new results about these numbers. Please interrupt me whenever you want to interrupt me. Okay, so what is the plan for this talk? So I want to start with some classical results, and by classical I mean up to 71. So there are some results around or before the year 71, and I call these results classical. So, and I guess no one of us was involved in these results. So you could also call them old results. So I mean, I still was at school at the time. Okay, then I will speak about randomized algorithms, then about tensor product problems and weighted spaces, and finally about CK functions and the curse of dimension. And this will take about 20 pages or so. So I have a lot of stuff which can be skipped or could be, I mean, depending on time and so on. Okay, let's start with this classical results. And the first result is by Smoljak and Bachwalov. And so in this result, we assume that Fd is convex and symmetric. So I mean, usually it's like a unit ball of some kind of a Banach space of functions. And if Fd is convex and symmetric, then it is enough to take such very simple linear algorithms. So adaptation does not help, and any kind of non-linearity of the algorithm would not decrease the error. And actually you can express this nth error bound in such a way, so you take the infimum over any n points from the domain and take now the sub over the integral where f is in the class, and in addition the function values are 0.
So I have a naive question. So as I understand information-based complexity, it uses the Bloom-Shub-Smale definition of an algorithm. So when you say that there's a statement about an algorithm, a computer scientist will say, what is an algorithm? And as I understand, the standard way is the Bloom-Shub-Smale definition of an algorithm.
Not quite. I mean, we need a little more, because we need function values. So we have the real number model. So we assume that you really can do such calculations with real numbers, like in a Fortran program. So you have real numbers, and you have plus for addition, and you can compute such a sum. You can multiply real numbers, but in addition you also have a kind of an oracle. So we need an oracle for function values. So it's an extension of the BSS model.
So when they wrote these statements before the BSS machine was defined, what did they mean by the word algorithm?
I mean, it's difficult now to ask these people, because also Bachwalow died, and so I'm not so sure what he meant, but it is basically a statement about the number of function values that you need, and I mean in this case I'm really a little. I find it a little strange that you ask this question, because here the algorithm is so simple, and I guess every colleague from numerical analysis would consider this as an algorithm.
So, is it correct that theorem means that any map that takes function values and outputs some number cannot be better than this simple linear?
Yes.
No, not algorithm, but any map.
So the word algorithm has nothing to do with the statement. That's my question.
Now, I mean, we have usually two notions of algorithms. So we have a very wide notion of algorithms when we want to prove lower bounds, and the lower bounds are much better and sharper if you have a wide notion of algorithm. And for the upper bounds, it is meaningful to have a much more restricted notion of an algorithm. But I guess everyone would accept such a simple computation as an algorithm.
No, this is definitely an algorithm, and everybody will agree. But what do you mean by all possible non-linear and adaptive algorithms?
It's more like mapping.
Yeah, exactly.
Yeah.
I mean,
This is smooth mapping,
no.
deterministic
All mappings. I mean, it is really in our books, and so it would be a little far to describe this, but it is really like this. You have what is an algorithm? So x1 is fixed. So this is really a constant in your program, because it cannot depend on anything what you did before. And x2 may be a function, could be a function of x1, but of course x1 is fixed, and f of x1. And it could be any function, I mean, it could be non-continuous, for example, and so on, and so on. And finally, so you have a sequence of such functions, and finally, the algorithm, I have it called an of f is any function again of x2 and so on fxn. And of course xn was a function of and so on and so on. So for the lower bounds we do not assume any conditions on those functions here. And I mean, here we are of course in a very lucky situation, because the lower bounds are so general, and the upper bounds are with the algorithm where really no one no, I mean, I know some colleagues who would not like such a thing, because we compute with real numbers, of course, and some people believe that one should compute with bits. So, and of course you can do a bitwise analysis of this stuff, but it would be a little boring, I guess. And usually we do not have problems with the rounding here, or at least it is very simple to analyze the kind of problems that could arise here. So it's not really interesting problem, I guess. Okay, I think it is more interesting to ask whether it is meaningful to have this assumption. And sometimes I guess it is meaningful and sometimes not. I mean, this is really a problem because usually you do not know the norm of your input, for example. You do not know the f, which norm has your function f. And then of course, it is maybe a bad assumption to assume the norm of the input is smaller than 17, because you simply do not really know. And there are other papers by, for example, by Fred Hickanel, Blaskota, Wasilkowski. I also contributed to this, where we have different assumptions about Ft. For example, one could assume Ft is a cone. And so the norm of f could be as large as you wish, and you have then a different theory and so on. But I really want to describe somehow the standard theory here, the basic stuff, because it's a basic lecture about IBC. More questions? Okay. So this was, by the way, this was a paper from 71, and this is why I put the date 71. There will be another result from 71. And this paper of Smoljak, I mean, it was not really a paper, it was his PhD thesis, and I do not know anyone who has seen this thesis. I think including Volodya. So it's a little shaky, and we all know the result because the result of Smoljak is also a part of the paper of Bachwalow. And so probably this PhD thesis of Smoljak, I mean, you know the old style where finally you were satisfied to have 2 or 3 copies, and you had to submit all the copies to the administration, and then it disappears. And so nobody knows this paper or this book, or I don't know. We know it only by the paper of Bachwalow. Okay. Now, another result of Bachwalow, I mean, so to speak, there are 2 results. One result is adaptation does not help. Adaptation does not help. This is the result of Bachwalow, and if you take the non-adaptive algorithms, then you can put it in such a linear form. This is just a Hahn-Banach argument. This was the result of Smoljak. So, but usually it's taken in this way together. Okay, another result of Bachwalow, even earlier, is about CK functions. So you have CK functions, and here the unit ball is given by this. So all derivatives up to the order k are bounded by 1. And Bachwalow proved that the optimal rate of convergence is n to the minus k divided by d. So this is a classical result, and I believe most people in numerical analysis know such results about the optimal order of convergence, and probably Bachwalow was one of the first to prove such a result. And for me it is important to say that this technique of Bachwalow really gives you only the order of convergence. So it does not give you somehow good constants here. So of course you have some constants here, but the constants are from above are so large and the constants from below are so small that that, for example, the lower bound, this lower bound, I mean, if you now take the number n of function values which is needed to compute the integral, you get, of course, such estimates. But here, these constants are so small that for a fixed epsilon you do not get anything. You only get n is bigger than 0, and this is what we knew already before, so this does not make sense. So if you fix epsilon and make d even larger and larger and larger, then this bound is completely useless. So this bound helps only if d is fixed, k is fixed, and really epsilon goes to 0 or otherwise n goes to infinity. And so this is really a result about the optimal order of convergence, but I mean, it is very questionable whether you can apply this result for something. So at least I would say it would be nice to know more about these numbers here. So this is not nice, because these constants depend on d and k. And these constants here on the left-hand side are much, much smaller. So they are exponentially small in d, and these constants are exponentially large in d. So this is not nice.
That was 60 years ago.
Yes.
This is what people were interested in that time.
Yes.
Asymptotic behavior with respect to n.
And I mean, this problem which I posed was solved 2 years ago.
This constant, yeah.
It will be at the end of my lecture. Okay, one can do this for arbitrary Lipschitz domains. I mean, to define algorithms, of course, it's much easier for the cube, because you can, for example, take tensor product methods. But to do it for very strange domains, it's more difficult. But you get the same order of convergence, and you get it not only for these classes, you get it for all kinds of Sobolev spaces, Biesov spaces, Triple-Lysoykin spaces, and so on. So Triple knows all those spaces, and we did it together in. It was
What
published.
about Hardy spaces?
Excuse me?
Hardy spaces, analytic functions.
No, I mean then you have a faster.
Yeah, then
Sure.
C infinity also faster.
Yeah, sure, yeah. And colleagues also discussed fractals, and then you get somehow this d has to be replaced by a kind of a fractal dimension. Okay. So this is an interesting result also from the historical point of view, because it is the first very explicit curse of dimension result, at least as far as I know. So the authors take Lipschitz functions, like I did already on Monday, and proved this very explicit bound for if n is of this form, then you have exactly this error bound, and it means a very strong curse of dimension. So if you want to decrease the error by a factor of 2, so here's 1/2 of here, then you have to multiply the number of function values by 2 to the d. So this is of course very bad, and this is in a very explicit form the curse of dimension. And usually this result is is connected with the names Sukharev. I first read it in a paper of Sukharev, but also Papienko and Chanaya have very similar results, but I mean, only a couple of years ago I found this paper. I think it's not much known. So it was published in Uzbekistan in a conference proceedings volume in Uzbekistan. So anyway, the result itself is not difficult because for Lipschitz functions you can easily compute what we call the radius of information. So you can easily get the worst function for given information, and then it is not too difficult to prove this result. Sorry. Okay. So of course this means a very bad curse of dimension, and this means you cannot really solve such integrals by deterministic algorithms. And now we have two possibilities. One possibility is to define much smaller classes of functions. I mean, this is really a very large class of functions. This Lipschitz property is a very weak smoothness property. So we can have smaller classes, or we allow more algorithms, we allow randomized algorithms, and I will start with this second case for randomized algorithm. And now, of course, AN, the algorithm, is now, of course, a random variable. So the output is random, and it does not make sense to just say the distance between what you want to compute and what the algorithm gives you. And what we usually take is this mean square error. So we take the mean square error, and of course in the special case when AN is deterministic, then we are back to the old error. And then we also define these numbers, and this run means, of course, randomized. And then you do not have this curse of dimension. You can even put the unit ball of LP, and if P is between 2 and infinity, then it's relatively easy, or it's possible to describe the optimal algorithm. It is of this form. It is almost like the standard Monte Carlo method. So you take IID xi on your domain of definition of the functions, and take such a random sum, and instead of the mean value you add a little constant here, and it turns out that this gives you the optimal algorithm. And of course for us it is important that D does not play any role here, so the dimension, so to speak, disappears.
Yes. But this setting is it's a very different characteristic than the one which you considered before. Because you take for each f, you take the expectation, right?
Yes.
In order to be in the same vein as before, you were supposed to take a supremum overall class, and after that take the expectation.
Mm-hmm.
Because this characteristic in a sense has nothing to do with that one.
No, I take here also the worst case
After you
setting,
take-
like before. I take the worst case setting like
Yeah, but
before.
after
The
taking the
worst,
expectation.
worst. So this holds for any f from the class.
Yeah, but
And this is what is done in Monte Carlo method.
Yes, but the sampling is done before you are taking the supremum. So
You can do the
Xi's are
sampling whenever
distributed
you want to
uniformly,
do it.
right? They're distributed uniformly, the Xi's.
In this case,
Random,
yes.
yes. Now, there is a tiny probability that you compute random numbers 1 million times, and each time it falls between 0.1 and 0.15, and the entire rest of the interval is empty. A very, very tiny probability, but it exists. So by taking the expectation before you're taking supremum, you're somehow smoothing over all these possibilities.
Sure. This is the whole meaning of Monte
Yeah, not
Carlo.
committing any crime, but I think it is important to say
Sure.
that this is
But I mean,
different setting.
this is what I said. This is what I said. You take the expectation. Sure. I mean, this is done since 60 years.
Nothing wrong about it. It is different.
Every page now will be different.
We hope so.
Somehow this is the idea of this lecture,
I think in most lectures.
not in all. Okay, now back to this class CK that we had before. Now again Bach-Wahlow proved this optimal order of convergence. So and here we get an extra 1/2. So the order is better by 1/2. And whether this 1/2 is good or meaningless, of course it depends on the relation between k and d. So if d is 1 and k is 100 or so, no one would care about one extra 1/2. But for example, for this Lipschitz continuous functions, you would get now the rate n to the minus 1 divided by d. This is for deterministic algorithms, and for Monte Carlo you get this extra 1/2. So of course it is much better. And you can do it also relatively easily with a unbiased estimator. So it is unbiased, and you can do it also in a way that deterministically you have the optimal rate of convergence. So because you can somehow you split your n, your budget n, your number of function values into 2 parts, and use half of them to in a deterministic way to find a good L2 approximation of the function, and then you compute by simple Monte Carlo the integral of the difference. So we have a good error control, and by the way, in some way Monte Carlo has really an advantage over deterministic algorithms, because you can run your algorithm a couple of times, and then you can do statistics. So you have here the real numbers, and you take the same algorithm a couple of times and make statistics, and then you get, so to speak, much more out of your computation than you get in the deterministic case, because in the deterministic case usually you do not know some constants in your bounds, in your error bounds, and usually you also do not know the norm of your function f in the space, and so it is usually not so clear whether you really can do a good error bound. Okay. So, but I will go back now to deterministic algorithms. So this was really only like 5 minutes about Monte Carlo, and I will go back to deterministic algorithms, and want to speak about tensor product problems, tractability, and weighted spaces. And so the first result is a joint result by many authors. There are upper bounds by Frolov, Skrikanov, and lower bounds by Roth, Bukovsky, and Temlyakov. And as you see, the whole stretch is about 40 years. So it took 40 years to prove this result. And the first results were, as well, the upper bound of Frolov was for p equal 2, and also the lower bound was for p equal 2. And of course, the upper bound is harder for small p, and this was done by Skrikanov, and the lower bound is harder for large p, and this was done by Volodya. And what is the class of functions? So we have a Sobolev space with bounded mixed derivatives. So now we have that the derivative, the alpha derivative of f in the p norm should be bounded by 1. But for all alpha, for all derivatives, where each coordinate is bounded by k. So you can, in each coordinate, you can independently have up to k derivatives. And so the highest derivative has the order k times t. So it's a very high order. And also this high order is bounded by 1. Okay, and then we get this nice order of convergence. And maybe you noticed I let out the cases p equal 1 and p equal infinity, because these cases are much more difficult and still unsolved. So it is not really clear what we have for results. And I find it very interesting that one can give one algorithm, of course, depending on the dimension d, but not depending on p and not depending on k. So one algorithm will solve the problem in all such cases. So in a way, this algorithm has a kind of a universality. So it does not depend on the smoothness k or on this integrability p. And I only indicate very, very shortly the form of this algorithm. So it is called Frolov algorithm because Frolov invented this kind of algorithm. And so it is for some very specific matrices. So you take the standard lattice here, the standard lattice in RT, and this is in a way rotated, and then also you multiply here or divide, depending on how you write it. So it is written here, the A is large, A tends to infinity, and then you get more and more points. So formally this sum is of course an infinite sum, but this is only for functions with compact support, so it is still a finite sum. And this matrix A again does not depend on K. And of course you have to use very special matrices. And you need then a kind of a transformation for the general case. So this only works for functions with compact support. Okay, another algorithm which is well known and famous is again by Smolyak. So this is sparse grids. Probably you know sparse grids or Smolyak algorithm, and it is also very good for this kind of problems. And you get almost optimal rates of convergence, but not really the optimal rate of convergence. So it started with Smolyak 63, and I think what you can get is this optimal order by Smolyak. And somehow the standard estimate, what is already contained in the paper of Smolyak, is here a 1. So k plus 1. And what the two colleagues did is to replace 1 by 1/2. But still, of course, it is worse compared to the optimal order of convergence. So this does not depend on k, just d minus 1 divided by 2. Okay, so these results were about order of convergence, and now I want to go back to tractability, and I would like to remind you about different notions of tractability like yesterday. So this is somehow the strongest case where we do not get any dependence on the dimension d. This is what we had for Monte Carlo methods and LP functions, and this is called polynomially tractable, weakly tractable, and so on. So there were two papers by Henryk Wozniakowski in '94, and after this many papers investigated these notions. So I discussed on Monday whether we can have tractability by smoothness properties, and I discussed the case of C infinity functions and approximation, and there was still this curse of dimension, but there's also at least one case where we can get tractability. Where we can get tractability by not really very strong smoothness assumptions. So usually we cannot get it, but here we get it, and I describe this result, which has a content, a relation to number theory. So we consider the star discrepancy. Star discrepancy means that we want to compute the volume of certain cubes or rectangles. So we have the unit cube, and we have kind of a box, and the box is described by this point T. It's here. And then the volume of this box is given by this expression here. So just you have to multiply the coordinates. And now you have a number of points, x1, x2, x3, and we count the number of points inside the box, and somehow optimal distributed sequence of points would have the property that this difference or discrepancy is small. And so we take the soup over all boxes, and this was studied by Hermann Weil and in number theory, but it is exactly a worst case error bound for numerical integration. Namely, you have to take this quadrature formula, and you have to take the norm, which is given here. So in the one-dimensional case, so you have just a Sobolev space. The first derivative is in L1, and you have a boundary condition. And for the multivariate case, you take tensor product, so you work with bounded mixed derivatives. And for these classes, or for the star discrepancy, one can prove that we have polynomial tractability, so we have the complexity is linear in the dimension. So here's a d, but not more, no exponent. So the number of points has to increase linearly in the dimension d. And there is a lower bound by Ik Hinrichs with the same d here. So the complexity is really proportional to d. And there is now somehow some people are working to improve the constants, and so there are more and more results, and I think now the optimal constant is 7 or 10, or do you know, Ik?
Between 7 and 10.
Okay. Okay, and at least those people worked on this problem. And so somehow the idea is, if you take random points, IID, random uniformly distributed points on the cube, and compute the star discrepancy, then the expectation is of this order. So you can also prove this result, so to speak, with the probabilistic method and just take random points. And here the bad news about this result is that everything is non-constructive. So we do not know such points. And I mean, I will, a little later, I will describe some results where somehow the first proof was also non-constructive, but a few years later constructions were found. And here it is not so. So here the result is already, how many, 15 years old? 17? 18 years old, and or probably more, because we 20 years old, and still we do not know a construction. Okay. So there was a very happy paper, a very good paper of Sloan and Wozniakowski that was cited hundreds of times, and they defined weighted spaces. So they made the spaces, so to speak, smaller, the unit balls smaller, by introducing weighted norms. So for example, in the one-dimensional case, you can define it like this, and if this gamma is very small, then your function has to be somehow relatively flat in order that you have a function in the unit ball. And we found that in many applications you have maybe hundreds of variables, but some variables are important and some other variables are not so much important, so you have only a small influence. And so one can model many properties by suitable weighted spaces, and then for such kind of Hilbert spaces, it is relatively easy to compute such a thing. And now I do something what you suggested, Volodya, namely I take random points from the unit cube, n random points, and I mean this is does not make sense. So we really have n points from the unit cube, and so the whole vector is formally, of course, in this high-dimensional unit cube. And then we compute the worst case error of the quadrature formula of this type, of such a type. We take the worst case error, and this worst case error is squared, and then we compute the expectation. And then we obtain this number. And K is the kernel of the Hilbert space.
Not the error.
Excuse me?
This is the quadratic error?
Yes. So this is a constant here. It does not depend on n, and this is the quadratic. I mean, this is the expectation of the quadratic error. And now, by this argument that we always use when we use this probabilistic method, then so we have a function. So this is our set of quadrature formulas, and we have the error of the quadrature formula, and we compute the expectation. Then of course there must be one quadrature formula where the error is smaller than the expectation. So the minimum is smaller than the expectation. So this is very trivial. And this is of course again only a existence result. And really in this very first paper they only proved such an existence. And later there came constructions. So this was continued, this work was continuous in many ways, in many directions, general weights, many different Hilbert spaces, also lower bound for arbitrary algorithms. Of course we want to have complexity results, we want to have upper bounds, and we want to have lower bounds that hold for all algorithms. And this is by the technique of decomposable kernels. And of course we want constructions and so on. But this is a very large stuff and history, and so there are many good books and survey papers. There's a survey paper of Dick, Kuhr and Sloan, and there's the book of Dick and Pilligshammer, and also a survey paper, and there are our books with Hendrik that contain a lot of such results. Okay, so finally I want to come back to the same class where we started. So this is the class of CK functions depending on the variables, and the norms up to the order k are bounded by 1. And we proved recently with Eike, Mario Ulrich and Hendrik that this kind of error bounds. So now we really have the curse of dimension. I mean, formerly before we did not know whether the curse of dimension holds for these classes or not. So now we know that the number of function values is basically of this form. And it is a little, I mean, you have to think a little. It is somehow trivial, but nevertheless. So the error is of this form. D times n to the minus k divided by d. And if you see it first, then maybe this d looks harmless, but it is not harmless because we are interested in the number of points you have to solve this for n, and so you have to put it on the other side, and then this d is not linear, but the d is to the power d divided by k. So it is really super exponential. And this is why this, of course, means that the problem falls under the curse of dimensions. So there is a curse of dimensions. Okay, I guess my time is over. I should stop here, and I would like to summarize. So numerical integration is intractable for classical function spaces like this. And now finally we have a good proof of this result, because I mean what we knew before was really only about the order of convergence. And what are the remedies? The remedies is we should have much smaller spaces of input. So we should study, for example, weighted spaces or problems with some different structure. I mean, also what we heard yesterday, for example, of course it is also kind of a different structure to assume sparsity. So this is somehow a different assumption compared to smoothness properties. Or we study randomized algorithms, and of course we can also combine the two things. Okay, thank you.
Questions? Comments?
Right. I think that there is something interesting going on. So let's go back to the Sloan-Wozniakowski theorem and this gamma i's. Yeah. So when the gammas are large, we have flat functions.
No, when they are
Small. So when they are small, we have flat functions. And somehow I find it very unsurprising, because we know from measure concentration theory that in very high dimensions, compact functions are almost everywhere flat. You know, they are non-flat on sets of very, very small measure, exponentially small measure. And so once you are imposing essentially that they are flat, you are simply removing all the bad domains where they are violent. And you know, Ian Sloan and I have this sort of vaudeville act. He gives a talk. By the end of the talk, I raise a hand. Ian looks at me and says, I know which question you want to ask. And I tell, yes, you're right. I want to ask again about measure concentration. So there is this wonderful theory of the measure concentration phenomenon that tells us that in very high dimensions, interesting things are happening, part of which are, of course, sparsity. The question is, to which extent is it possible to take this into account in, for example, integration where d is very large, say 100, 200, and so on?
No, I did not put it here. I'm not sure what you want. Do you want to have a different interpretation of our result, or do you think our result is wrong, or what do you want to say?
No.
I mean, because let me say, here is a statement. It says there exist such points such that the problem is strongly polynomial tractable if and only if. If and only if. So this means in some cases, for some Hilbert spaces, they are simply too large, and you can have measure concentration, yes or no. I do not care, but the problem is too difficult. You cannot solve it. You need exponential many time, and so there is no way to solve the problem. And in other cases, if this sum is finite, then you can solve it. And I mean, it is not.
Okay, so
It does not
let
help.
me tell you
This
one possible.
measure concentration does not help for this problem.
No, no, so
I would claim.
let me tell you how it can help. It is go back to the definition to the what we raised earlier of first taking the expectation and then taking the supremum. If you invert the order, you first take the supremum, then the expectation, then measure concentration essentially tells you that in one probability 0.9999999 you can get, or whatever, you can get the answer to very high accuracy, but there is a tiny proportion of problems for which you will get complete nonsense. And for practical reasons, this is not tractability anymore. It is some sort of a relaxed tractability.
I mean,
But for practical reasons, many people will be very happy with that.
let me tell you something which Eike will explain next week better in his lecture. So now you want to invert the expectation. Now you want to take a deterministic algorithm, AN, and you take its worst case error over some class FD, and now afterwards you take the expectation, and now you can ask typical algorithms, or you could say, is random information almost as good as optimal information? Because, I mean, it is clear that the optimal algorithm is of course better than if you take the expectation of over many algorithms. So if you take the optimal information, then of course it is clear that random information is maybe a little worse or much worse. I mean, depending on the problem. And I think we have very surprising results. So in some cases, it turns out that random information is almost as good as the optimal information, but we also know cases where random information is very bad and gives you nothing.
Yeah, but basically this supports his idea. This is a result of this concentration of measure.
Maybe I can add something. In this connection here, concentration of measure is really important. It's behind the results, because then you somehow, this is an expectation of a supremum, right? Of some kind of random process. So empirical process theory, something like that, enters in those things. But in the question Erich had today, this is kind of different. What you do is you have different variables, and by the gamma I, by these weights, you somehow moderate the influence. As you said, if gamma I is small, the function in that direction is somehow flat. Okay? But this has not as much to do with measure concentration.
Yeah, it's a little different.
It's,
but in the
it's
sense
different.
that-
It's more like truncating.
Yeah, but
the
in the sense,
dimension,
in the
right?
following sense, that this is what Ariel started with, that when gamma is small, that means in that direction, in that
You have a
variable,
flat
it is
function,
flat.
yeah.
Yes. And basically, this is like if you have many flat, that means you don't care. You just
Exactly,
truncate
right,
and you
yeah,
get. So it's not exactly like you
It's
said.
not
this
exactly
one,
measure
but close.
concentration,
Yeah.
but the idea is somehow the
The
same.
intuition
Yes.
is the same. Other questions? I have a little comment for the previous page, number 18, for this discrepancy. What you mentioned. Yeah, you said that talking about constructions, I understand that you are talking about explicit constructions. I mean, to give an explicit construction that you should. Yeah, I don't know that either, but what I know that the result a little bit weaker than that, but still in terms of tractability is the same. It's polynomial tractability. The inequality like that can be proved constructively using greedy algorithm.
I think we have discussed this many times, Volodya, and I mean, there is a constructive part of mathematics, and it says if you have some algorithm, then this is construction. But we are, I mean, in this sense, we are really more practical. So
Yeah, but this is
the
different
problem
story. You
is
wanna talk
about
about
running
complexity.
time.
You want to talk about complexity.
And the best running time, if you really want to construct the algorithm, I think the best running time was done by people like Michael Knevo, but even this algorithm has exponential running time, and so it is not really, I mean, it is constructive in a theoretical sense, but not in a
But
practical
anyway,
sense.
this is the difference. I mean, when you're talking about random, it's just an existence. Indeed, you don't have any construction.
We also have a construction. It is very simple because we can, by random, we can have a discretization of our grid, and then,
Not a construction.
of course, it is a construction. You can run an algorithm, but this algorithm will never finish. I mean,
Yeah, but in
like your algorithm, it always will
the
not
greedy
finish.
algorithm finishes, and it gives the constructive way to prove that.
So please write a paper and do this stuff with d equal 20 and n a few hundreds. You will fail probably.
Your constructions also have this exponential construction time, and this is a
This
problem.
is a different story.
No,
it's complicated, but it is constructive.
This proof here.
No,
This proof can also be done in a discrete grid. And then you have an algorithm which just is look at all finitely many point sets
But this
in
will
that
not
grid.
prove anything. If
It
you
will
say
prove.
that
You can-
okay,
it
they,
will
that
prove.
exists,
No.
then let's take that. But this does not prove.
Yeah.
It's not a proof.
It is a proof. It is a construction.
No, it's not a
It is
constructive proof.
It is a construction.
You use that and then you. Yeah, okay, but let's talk about that.
Okay.
Let's not involve everybody. Other questions?
Maybe I can ask a question.
Go ahead.
What is a construction? Okay, and I will answer the question myself. Okay, so a construction would be something which gives you a point set, a sample point set, and proves that this point set has satisfied the error bound you want. Right? This is what your greedy algorithm does.
Yes.
Okay, and this is what you can also do with a discrete grid. Just look at the point sets in that grid and compute the error. You can compute the error exactly in finite time. The running time is exponential, doesn't matter for you. Okay, the running time is exponential. This is a proof of this result, which is constructive in your sense, and this is not what we really want. We would like to have polynomial running time in the error and in the dimension.
In your proof, you will have the following step. You take this discrete,
Yes.
and now you say that each of them, I mean, so close to each other that the minimum over this discrete
Yeah.
is close to the whole minimum.
That's enough.
But for the
Error bound.
minimum, you say this guarantee.
Yes.
And this
Guarantees-
part is random. That means it's not a constructive proof.
It is. In the same sense as your
You
greedy
use,
algorithm.
you use a randomized argument.
In your greedy algorithm, you also just claim, okay, the minimal, but you have to find
No,
it.
no,
You
no.
have to find it.
No. In grid algorithm, it gives you the algorithm step by step. You do this, you do that, you do that.
I just give
Our algorithm
just
is
give
also
the
step
same
by
thing,
step.
Wolfgang.
Every
Just give
algorithm is step by step.
Yeah, but the argument,
I know
in
all
order
those
to
papers.
prove the argument, you need this randomized argument. Otherwise, you cannot estimate this.
You can compute it exactly.
No,
You have a finite number of point sets, you can compute the error exactly for each point set. After the 5th or the 10th point set, you have a point set which gives you this. Okay? This is constructive, of course. In the same way as your greedy algorithms. So we discussed this several times.
Okay, let's talk about this later. I mean, other questions? Okay, then let's think.